It's got a picture of an HDMI instead of a laptop. Sure. Consistency, who needs it? All right, you don't need to worry about that asset. That's for something else. Okie dokie, and I'm just going to open up my lecture slide, because I was thinking that just before I got here. Teaching 244, week 11, has this synchronized 11:35. Oh my gosh, is there no Wi-Fi? Oh, I've just turned my Wi-Fi off. Whew, whew. We're about to get started. This is going to be a pretty full-on, intense lecture because there's a lot to cover, but hopefully you get something out of it. Now I'm just going to check to make sure, is this syncing all the stuff I want to sync? 11:35, that's probably good enough. Is it the 7th today? It's the 7th. Alrighty. Ah, cool, it's going to download a new version. Oh, thank you, OneDrive. Sorry, I was writing these lecture notes right up until the point that I came over here, so you're getting the tippity top, you know, the absolute best version of them. Just ignore the spelling mistakes. Yeah, some great Wi-Fi in here. I shouldn't have put all those videos in. All right, turn that off. Okie dokie. So, where has my mouse gone? There we go. Today we're going to be talking about Unreal Engine 1 level optimization, which is going to be super important for you guys as you make scenes going into your next project, I guess, or your next assignment. I am Lee Beattie. You might have seen me floating around. I see a lot of familiar faces in here anyway, but I'll introduce myself regardless. I'm the SOPD game design technician, or I think this name is actually going to change to specialist because technician doesn't make sense with regards to all the other technicians we have. I don't like seeing my face that big. It's really weird just standing here looking at it. But I've worked in the industry professionally with Unreal Engine for 6 to 7 years, making AA and AAA games. I write a lot of different programming languages. But I also specialize in a lot of different areas, like engine programming. I've worked a lot inside the engine, but most relevant to this course is going to be rendering programming and tech art. So if you have tech art questions, you can always come and ask me. Examples of games I've worked on is things like Depth. You might have seen it before. It's a New Zealand-made game here in Christchurch. It is a sharks versus divers game, multiplayer online. 2 shark players get to fight 4 diver players, so it's got this duo this asymmetric game style of people who are playing as a power play, which is a shark, and people who are playing a horror game, which are the divers, as they get hunted by the sharks. I've also worked on Fortnite, so if you've ever played the creative game mode in Fortnite, I put a lot of effort into that, into making devices that actually allow you to make your own game types. So if you've seen things like the vending machine or the teleporters or the item spawners, etc. I worked a lot on those for Epic Games because, again, our company in Christchurch got contracted out to Epic Games to help them work on the creative mode. So I do know a bit of my stuff. I've also worked on Chivalry 2, doing shit work for them, just debugging all the stuff that they didn't want to debug and fixing all the problems that they didn't want to have to deal with. So that's on the Xbox in the LecA game lab downstairs. I've also worked on a game called Maneater. See a bit of a theme going on, a few shark games. That one came out on Switch and PC. I made the save game system for Switch and blah, blah, blah. Nothing super exciting, but I've worked. I've been in the industry. I've done a lot of stuff with Unreal Engine and its renderer and a lot of the engine code. So what am I currently working on? I'm currently working on something called Surreal 98, which takes Unreal Engine 1 games from the year 2000, and at runtime, it will translate them to Unreal Engine 5. So this does a lot of graphics and material and shader stuff at runtime to dynamically teleport that over as the original game is running. You're actually seeing the 2 games run side by side on the same monitor. So you've got Unreal Engine 1 on the left and Unreal Engine 5 interpreting its data on the right. So yeah, that's pretty exciting. So that's going to be, I'm going to patch that as a way of automatically remastering games in the future, so because it just does it automatically and it's really authentic. So if you don't know where I am already, come and visit me. This is, you might have already seen this lab already because you've done your labs here. I have a little office in the corner and you can see the little Mac there just sitting there. That's usually a sign that that is my office. You've got the right door. I am also the Magical Fairy on Discord, and here's my email address up here. Cool, introductions out of the way in 4 minutes. So let's have a look at what we'll be covering in this lecture. So There's a lot to talk about. Unreal is quite complex, like most engines, and it'll actually scale up and down quite a lot. But I think we need to touch on some higher-level concepts first, like the minimum viable product. And then we'll go into these more specific things about the engine and how you can take your scene that's running like crap and turn it into something that runs like silk. Cool. So first we'll talk about how organizing your content. We'll just cover this as a basis to start with before we get into more technical stuff. Because as you're working on your scene and you're adding more and more static meshes to it, more lights, etc., you're going to find it's going to start getting quite complex, and the world outliner, so this is part of the editor, you've probably seen this before, is going to start getting quite full of stuff. But you have folders, and you can put folders in folders, and you should start organizing your content into these folders. For example, you could have geo means geometry, so geometry would be things like static meshes and skeletal meshes and all that kind of stuff. And you want to organize it by, I don't know, you've got a thing in your scene that's a house, or you could have house 1, house 2, and then you could organize it by room. You can do that. You need to figure out a system that's going to work for you, and it's going to just help clean up your level outliner so that it becomes easier to work with. I fully believe in you're not just making a thing, you're not just making a level, but you're also making an experience for other artists that are going to use your level. Just like code. And you want it to be easy for them to use as well. So use nice names, organize it nicely, and you'll find that your art workflow in a team is going to run a lot better. Because everyone's not going to be coming and asking you questions of where's the blah, 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 what's the XYZ, etc. If you organize it nicely, you save time in the long run. So one other thing we're going to talk about, and we're going to start getting into some of the specifics now, is you want to start putting things in sub-levels. So, Unreal Engine has this concept of sub-levels. This is like, it also has a concept of layering as well. You can layer things, but sub-levels are probably a nicer way of doing it that you can also exploit while the scene is running as well. So a sub-level is basically its own asset. So you've got a level asset in the content browser, right? You double-click that, opens a level. You can make other levels and layer them on top of each other. So you could have, for example, a sub-level that just has all your lights in it. So if you just want to load in the lights level, you can mess around with it, whatnot. You could also have one that just has your landscape in it, or it has a certain props. Or you could divide up your map into quarters and have those as sub-levels and layer them on top. The nice thing about this is because I understand for the assignment, you're going to have different lighting scenarios. So you should have a different sub-level per lighting scenario that you want to have. So like daytime, nighttime, put them into their appropriate sub-level. And you want to go in and go to the window menu up the top there and select levels, and that will give you an overview of the sub-levels that you have. Don't worry, we'll do a demonstration. Yes, and here it is. If you open the window for levels, this is what you get here. You get something called the persistent level. That's like your top root level, and then you start adding sub-levels to it. So in this scene that I've got in the background, I've got multiple sub-levels. You can see I've got, well, you might not be able to see because it's tiny, but it says space junk FX. So FX is usually things like your particle emitters, ambient fog volumes, color correction volumes, etc. I've got underscore geo, that's all the geometry in the scene. We've got underscore lighting, and I don't know what underscore P is. I'll have to go back and have a look at it, but I don't remember. And while you also put things in sub-levels, you can also limit the level outliner that we looked at before to just the sub-level that you have selected. So if you're just working on lights, you can limit the outliner to just the lighting sub-level, and then you'll only see lights in the outliner, which makes it handy just to really easy scroll around and see what you're editing. Sub-levels can also be loaded and unloaded at runtime. So in the demo that I have 1, 2, and 3 are bound to loading different sub-levels for different lighting scenarios that can show you how different ones perform while the game runs. So let's do a little demonstration of just the folders and the outliner. So I used to have a problem with this. I've got to end my slide first, and then we're going to open up the editor and have a look. So let's go to D drive. Am I up on the screen? Cool. And we're going to go to PROD244. We're going to open up my test project here. So the thing that I have actually comes from as a sample asset you can download on the Unreal Epic, the Epic Games launcher. It comes with all these great assets you can play around with, great materials. It looks fantastic. And this is a virtual production test environment. So we'll just let that load and open. I compiled all my shaders before I got here, so that's a positive. Let that open. Cool. So we've loaded into our scene now. And you can see on the right-hand side here, everything is kind of organized into these nice folders. Can everyone see that? Is that visible up the back? Sweet. And we've got different, but there's nothing in these folders. It's because I have this limited to only in current level. So that'll limit what shows up in the outliner to what level I have currently selected. So I'm going to turn that off, and you can see this level's actually got quite a lot of stuff in it. So I'm not limiting the outliner anymore to just the level I have selected. But if I go to Window and go to Levels, you'll see that I've actually docked the Levels window down here. So I'm just going to bring it up. It's just a floaty window, and you can see I've added 2 extra levels compared to what are in the notes. So I've actually got different lighting scenarios for dynamic and super static lighting. So if I just double-click on my dynamic lighting scenario and I limit, I added a folder, that's not what I wanted to do, let's delete that. I want to limit to only in current level. You can now see these are all the items that are in just that sub-level that I picked. So if I go Window, Levels, you'll notice it's highlighted in blue. That means that's the one I've got selected. You can also select one from down here. And this, when you get sub-levels, you get a little window down here that allows you to just pick sub-levels that you want to work in, so you can really quickly switch between them. But you can see now my outliner is just limited to what is in this sub-level alone. And it's just lights, because it's a lighting level, and I can click around and do stuff to them. So that's a great way of organizing all your assets into sub-levels so that they make it easier to work with. Was there anything else I wanted to demonstrate with that? Okay, so if you want to create a new sub-level, you can, in this Levels menu here, so remember, Windows, Levels, you can create new or add an existing sub-level. So we can just go Create New. And you probably want to pick empty level because you don't want anything in it. You don't want basic, you want empty, create, and then you just pick a place to put it. So it should probably exist around all your other levels as well. So they have this one, stages, yeah. We'll just put it in here and we'll go and we'll call it my new sub-level. And bam, it's ready to go. And it should already be added to your persistent level as a sub-level that you can use. And you can start editing it and placing things in. And now I have it selected, it's in light blue. You can see there's nothing in the outliner because I've limited my outliner to only show what's in the current level. Remember, if I turn that off, I get everything that's in all the level and the sub-levels. Cool. Right, let's move on. I feel like this is an older version of my demonstration. No, it's not. Good. Fantastic. All right. So, what is wrong with this pocket knife? Would anyone like to tell me? Too many tools. It's over-engineered. So it's got absolutely everything you could possibly want with a pocket knife. The engineer decided, my guys are going to need everything. I don't know what scenario they're possibly going to use, but I'm going to add every single possible thing you'd want to a pocket knife. But you can see now that it is quite wide and it no longer fits in a pocket. So that's the actual problem. It won't fit in a pocket. So you, with your scene, have to figure out something called a minimum viable product. You don't want the pocket knife, you want a pocket knife that fits in the pants. So when you're making your scene, your assets, your lights, you'll encounter an anxiety of everything having to look perfect. But that actually just leads to overcompensating on things that don't actually matter and actually going to cost you a lot in performance. So optimization is about focusing on what truly matters. What is your user going to see? What are the people viewing your movie going to see? What are they going to focus on? 99.9% of your viewers will not notice that the dynamic highlights on your mountain stream that is 50 kilometers in distance doesn't move. They don't care because there's a dude like dancing in front of them or whatever. And that's what actually matters. You need to focus 100% what's in the foreground because if it lacks good lighting, your users are going to complain. They go like, that looks shit. And that's what you want to optimize. That's where you want to focus most of your resources. So don't spend it on the mountain in the background. Bake it out. Do whatever you have to do to make it super low cost. Because we don't over-engineer bridges with absolutely every safety feature that they could possibly ever have. We only engineer them with what they need so that they can stand up to the safety requirements of what we have. Because everything has a cost. When you do art, it has a cost, and that cost is time. And it's nicely highlighted in this color here. So focus on what's important. So, okay, your project is super slow. So we're going to figure out how did you get there? What's gone wrong? And usually that can come down to an improper selection of rendering technologies. So we're working with a runtime renderer, so there's a lot of scalability and things we can configure. Your assets are overdone. I probably want to put poorly in here, but poorly is not the right word. It's just that you haven't spent enough time focusing on what matters with your assets. And your level is not optimally set up. And we'll cover all these bases. So how do you tell what's going wrong? So the amount of times that I've worked in industry and people have said, I know what's wrong, I'm absolutely sure it's this thing, and it's just a guess. Because they added a thing, things started going slow, and they're like, oh, it's got to be the thing, it's got to be that thing. They're usually wrong. So what you want to do is you want to profile. You need to base your focus and what you're going to fix based on data, based on real facts. And then we're going to go through how do we fix it. So my biggest suggestion that I give to programmers, and this will apply to artists as well, is slow down. Because as you speed up, and the anxiety of wanting to get stuff done quick is actually going to make it harder for you to accomplish what you want in the long run. So slow down. Read a little bit of engine documentation, because it's there so that you can gain wisdom, and in the end you actually end up saving time. Because you're not just fiddling with settings for 2, 3, 4 hours and going, what's wrong with my project? Read the docs. Because usually it'll say like, oh, don't use this. If you use this, it's probably going to mess up. It's going to go super slow. And they're all out there. Go to the Unreal Engine documentation online. And then, how do we tell if my fix has worked? Profile it again. Yeah, keep testing your scene through the profilers. So, let's understand real-time rendering. So a lot of you have been working with Maya that has an offline renderer. You've got all the time in the world, well, you don't really, to render out your scene. But it's not required to be real-time. But at the moment, we've got a very limited budget on how much time we can spend rendering a scene. So real-time rendering is less elegant than ray tracer. It's a whole bunch of hacks just layered on top of each other to make a scene kind of look cool. But it's a combination of decades of research into real-time rendering. And basically, all that research is just trying to figure out how do we cheat? How do we make it look like the thing is there? And because they cheat so much, they're extremely fast. But that means it comes with caveats. And it also means they become complex to configure. Compared to ray tracing and path tracers, which are just brute force, but they have an elegance to them. You cast out a ray, it bounces off stuff, and then you get the pixel result back. Runtime renderers are generally not like that, but they are moving towards ray tracing. Yes, and yeah, the configurability of our real-time renderers means we can actually scale them really, really well. So they will scale to different types of hardware or necessary needs that we have just based on the settings that we put in. But I think the best way to understand real-time rendering is you need to get into your mind this idea of static versus dynamic. Because cheating involves just not doing not doing too much work. We don't want to do work that's unnecessary. And real-time engines have this concept of static and dynamic actors and objects and effects in their scenes. So static elements are generally considered faster and dynamic elements are generally considered slower. And the reason that is because static elements basically means you only have to compute something once, and once it's done once, we can just keep reusing that result forever. Dynamic means it has to really react to everything that's in the scene, and the level, all the lights that are moving around, the shadows are changing, the players are running. Those are kind of your dynamic elements, right? And they need to be computed every frame because they're changing. So yeah, if we set up our static and dynamic elements properly in our scene, we can gain a lot of performance back. And this allows the engine to pick a proper rendering path for our objects in the scene. So that's probably another terminology that will be important to you, is this rendering path. There's paths that are considered slow and fast and optimal. Cool. So let's have a look at some static elements. Static elements are assumed to not update every frame. So that not update is very important. And some of their work can be pre-calculated. We can even do it offline before we even run the game. Super, super important. And because they're pre-calculated, we can't update them once they're in the game, basically. Once they're static, we can't start changing them at runtime. So your level actors, your lighting effects, your shadow effects, your visibility can be pre-calculated. So when you're moving a camera around a scene in a game engine, basically it has to try and figure out what's in front of me, what's in the view frustum, and what am I supposed to render right now. And that can actually be quite expensive in itself. So you can actually pre-calculate what's visible from a certain point of view before you even run the game. So there's visibility volumes that you can add in. Well, how much time we got? Okay, we're not doing too bad. So dynamic elements, yep, generally calculate their visual effects every frame. So they can be slower than static effects, because the computer's got to do all that work to calculate all these dynamic elements. And some dynamic effects can actually take several frames to calculate. So you'll start hearing the word temporal a lot in rendering. That just means it takes time. It can be a time of 1 frame, it can be the time of 5 frames, it can be several seconds for certain effects to resolve or to calculate. But yes, because they update every frame, you get more dynamism from your visuals. So if you actually just flip between these two slides here, you can see there's a bit of a difference between the specular highlights and the dynamic scene, static scene. The static scene still looks great, it still looks really good, but if these have to shift, if all these specular highlights have to move, maybe we should start considering some dynamic lights that are in our foreground, focus on what's important in front of us. We can generally get better reflections out of a dynamic scene rather than a static, but you can also mix and match them, so focus on what you need to do. So our minimum viable product simply is how do we cheat so nobody ever notices? That's basically it. So let's talk about cheating. There are 2 main paths to optimizing with real-time renderers. We can optimize our engine settings, so there's a lot of features you can optimize by just turning them off or changing their settings that will affect the fidelity of your visuals. And there's asset optimization. So this is the other half of what you'll be doing. So things like, I put texture resolution at the top there, it really needs to be at the bottom. But if you're limited on memory, texture resolution can be a player in, your performance. Like, does that rock in the distance? Again, at 50 kilometers away, need to have an 8K texture? Probably not. So we can probably minimize that to go easier on the texture streamer. Light settings, so yeah, this is where you can probably get the biggest gains because shadowing is really, really expensive. Dynamic shadowing is super expensive. And then your surface material complexity. So you guys have been writing materials and you've been putting them on bottles and spheres and stuff. That's a surface material, basically. And the complexity of that can also count to how quickly the GPU can get stuff done. All that code is usually run at runtime while your game is running. So, let's actually see what a real-time renderer looks like. Let's see if this demo is going to be an absolute failure. So we'll just close the editor for now. And I have this, it wants me to save, but I didn't really change. Oh no, I added that new level. Let's not save it, we don't really care about it. So I have this tool called NVIDIA Insight. And this is usually why, these tools like this are why we usually buy NVIDIA graphics cards for the labs. Because they have the best debugging tools in the business. So I've set up a profile for PROD244, and what this does is it runs our editor, but it allows us to stop at mid-frame and actually see what's going on piecemeal about how a frame is built. And I'm going to click keep, it's going to come up with a whole bunch of warning messages, I'm going to click cancel, cancel, cancel. Don't worry too much about it. If you sign up for an NVIDIA account, you can download this tool yourself, and it's super helpful if you want to go super deep into profiling your scene. But I think in this scenario, it's going to be super useful just to see how a scene is built. So I'm going to close my level view there, and you can see there's a little frame counter up here at the top right. That's put there by NVIDIA Insight. But what I'm going to do is I'm going to toggle immersive mode. We're going to go full screen. I'm going to press G. So G toggles between game mode and non-game mode. So this is editor mode. You can see all your little widgets in the scene that show you there's a light here, there's a thing over there. But if I press G, I just get game mode. So you can see it's quite laggy at the moment, which is going to be super important for us later. But I'm going to press F12 to capture the frame. And you can see it's stopped. But what it's actually doing in the background is now capturing the frame for me. So we'll let that do its thing. Yep, click cancel. Don't worry about that. It's all good. And once it's captured our frame, we can actually start scrubbing through it. Some of you might have already seen this for Unity profiling. Yeah, so we get a lot of data here. And we're actually going to alt-tab back into the NVIDIA Insight Graphics Replay. And we actually have a little scroller thingy down the bottom here that we can scroll through. So a frame is built up with lots and lots of meshes rendered multiple times. And depending on the settings, oh my gosh, depending on the settings that you pick for your game, this can get more or less complicated. Oh man, I wish that wasn't in the way. But you can see here, like to start a scene, we have to just build up something called a depth map. So, and that allows us to tell the GPU what's in front of everything else in the scene before we actually start rendering real pixels. So that has to happen first. And that's why visibility is a really hard thing to calculate. because we had to figure out this. Then we had to do an occlusion test. You can't really see anything from that. Then we had to start calculating all these weird maps. So this is how GPUs are cheating. They're calculating all these weird textures that don't make much sense to us, but when it's incorporated in render settings in the background, it can actually it results in pixels that we actually want. This is all like shadow map data. I believe since we're using a light map, we've baked our shadow settings into a light map. These are all the different parts of the atlas where it's resolving different shadow detail for different meshes, so it can look up into that. Cool, cool, cool. Let's keep scrolling through it. And now we can see this is where your code comes in. So this is called the base pass. So it's actually rendering, it's quite dark, but it's actually rendering all those surface materials into render targets. Oh boy, that doesn't look great, does it? Oh, it's doing nanite, blah, 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 blah. Oh no. Not a great demo, but you can kind of, oh, it's so dim that you can't see it. But you can kind of see in the background, this is where it's actually rendering in all those material properties that you're outputting. Oh no, it's with the debugger, don't worry about it. Oh, the lighting? Lighting, no, that's the microphone. Lighting. So we're going to go front. Alrighty. But it doesn't matter too much. And we can actually see in here we get a lot of performance data. And we can see that shadow depth takes up a large chunk of our performance here, 33.8%. And your base pass that you would have written is currently taking up a very little amount. And this is where we can start focusing on optimizing our scene. But you won't have to use this tool. I'll show you how to do it in Editor. So I'm going to click Terminate, just close the program, and we'll go back to the notes and start talking about what we can do about it. Nope. All right. So let's start off by talking about settings optimization, first part of your optimization pass. And you have to start asking yourself certain questions. Is it okay that our level uses baked lighting? The answer is usually probably yes. If you don't have a dynamic day-night cycle, if you've got a static, if the sun's going to stay in the same spot in the sky, you should probably start considering baked lighting because that's the cheapest kind of lighting that you can do because you do it before the game runs. You bake the lighting in the editor and then you deploy your application or your scene and then it's all just pre-calculated. But if the answer is no, you might start considering things like Lumen, which has a higher runtime cost than baked lighting. Everything has a higher runtime cost than baked lighting. So Lumen is a global illumination method that runs at runtime. It's fairly efficient for what it does, and it has reasonably good results. Path tracing is not feasible at runtime in Unreal Engine and has the highest runtime cost. However, this will change in the future. And if you've seen the preview for Unreal Engine 5.5, it has a thing called megalights. That actually allows you to do hardware ray traced lights fairly quickly at runtime, and you can have as many lights as you want with as many shadows as you want. But that's not currently a reality for most of us, so we have to continue on with what we've got. So, global illumination settings, I've just put some screenshots up there for you for where you can find these settings. So if you go to, I'll just reopen my editor. So if you're in Unreal Engine's editor and you go Windows and you go, or is it Edit? It's probably Edit and then Project Settings. You can find this setting up here. So global illumination allows you to pick if you want a dynamic global illumination method. If you're going to go for baked lighting, just go for none. But if you need more dynamism to your scene, pick Lumen. And this setting applies project-wide, but you can also override it with something called a post-processing volume. So that's a volume you can put in your level to override post-processing settings. You can override the global illumination method for whatever is inside that volume. Let's go have a look at it real quickly, and we'll see what Lumen actually does in the scene. So you can kind of get an understanding of what's going on. So what I'm going to do is I've got my dynamic lighting scene up at the moment, so that's perfect. All the lights in the scene are fully dynamic. And what we want to do is we want to go to, take my project settings. Oh, I want to take it out of there. I'm just going to put it to the right and we'll go left. And in my project, so remember, edit, project settings. And there's a search box up the top here. You should just be using the search box. Don't fiddle around scrolling through here. And all you have to do is type global, and there we go. So we can see that our global illumination method is set to none. So if I just switch to my dynamic level, have I set it in the post-processing volume? Probably. And I could also search in this search box as well. We can go global illumination method. Oh no, we can't. It is global Oh, I'm on the world settings, of course. I was in the wrong window. Sorry, my bad. So on the post-processing one, global, there we go. Global illumination is currently set to lumen. So what we'll do is we'll look at this scene here, which has a lot of bounce lighting in it. So global illumination is when light hits the surface, it can bounce off and then light other surfaces, which is usually quite expensive, which is usually why you bake it. But if I set it to none, you can see a lot of that global, that bounce lighting has disappeared up in that scene there. I'm just going to make sure all my levels are set right. It is just that one. Yep, cool. And you can see this doorway here doesn't have as much bounce lighting in it, so if I switch lumen back on, you can see, oh, now it lights up a bit, so we get some of that bounce lighting going on. And you can configure the settings of lumen in here as well, so lumen global illumination, if you just click tick, you can start overriding settings of it, so if you want higher quality, view distance, blah, 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 max trace, all sorts of stuff that you can look up online to figure out what they do and play around with them if your scene isn't looking quite the way that you wanted it to. If we turn it off none, yeah, you can see that whole section there now goes dark because there's no light bouncing into there anymore. So lumen is cool, but yeah, it has a cost. And you can achieve the same results with baked lighting as well. It just means that they won't change over time. So, another setting that you can optimize is something called dynamic shadow maps. So dynamic shadow maps is when you've got dynamic lights in your scene and they don't bake their shadows out. There's different methods for doing the shadow mapping of those dynamic lights. If you choose the dynamic lighting route, you'll find the shadows might start penetrating, or the light will start penetrating and leaking through surfaces. And you can improve the quality of them by using virtual shadow maps. And we will look at those in a second. You can also try things like tweaking the shadow bias on your lights. So if you click your light in the scene, there's a little setting there for shadow bias. You could fiddle around with that, but it could affect other things in your scene as well, and they might start looking bad. So virtual shadow maps work well with nanite geometry, which we'll talk about soon. So make sure your project has nanite enabled, and if you do choose to go the virtual shadow maps route, make sure your meshes also have nanite turned on as well. You can bulk turn them on if you want. I can show you that if you want. Also, warning, changing these settings causes a recompilation of shaders. In 5.3.2, that's like 7,000 shaders that need to compile, so depending on the computer on it, could be 20 minutes of waiting, 5 minutes. Unreal Engine 5.5 is like 3,000, so it's way quicker now, which is nice, but we don't use 5.5 yet. So let's have a look at these settings in the editor and see what they do. So we'll end the slideshow, and we will tab back to our editor. And you can see that the shadows in my scene are actually kind of crispy. That's because, well, maybe you can't, but we need to see a comparison, don't we? But that's because I have turned virtual shadow maps on. So in my project settings, I will go shadow is my search term. I'll scroll down, shadow map method. So if I turn this to shadow maps, which is the traditional way of rendering shadow maps, you can see it's kind of shittier looking. And this should be shadowed here. There's a lot of bleed going on. So what I might actually go and do is turn my engine scalability settings, which you can access up through the viewport here. So this is like if you were to go into a game, you set low, medium, high, very high settings, that's this. So I can set it to epic, and you can see my shadow maps got better, but also worse. Okay, cool. So what if I changed my scalability settings to cinematic? Still doesn't look great. So what I can do is, if I have these problems and they're quite bad, and I don't want to bake my lighting, and I can pay the cost of virtual shadow maps, I might just click it, turn it on, and boom, we just get these really, oh boy, that's laggy. Let's turn the engine settings back down to high. There we go. But I get these really, really nice shadows going on. If I go to so this is going to be quite important to you. You'll always look through these optimization view modes here. These are quite cool. But you can also visualize the virtual shadow maps, and we can actually just go have a quick look and see what they do. A virtual page. What they do is they dynamically scale the resolution of the shadows based on how far away you are from a thing, about how much resolution it thinks it's going to need. And it just uses something called memory paging, don't worry about what that means, to give you resources to render those shadows nice and crispy. So it just gives us really, really sharp shadows up front. Actually, a really good example of them is actually over here. We've got some nice shadows on our rocks here. And if I turn that back to shadow, nope. If I turn that back to shadow maps, boom, they're just all gone. It looks gross. It looks like Gears of War 2005. Boom, there we go. So it's a judgment call up to you whether you need this or not. If you're sitting back here and this is your scene, it doesn't really matter because we're not that close to the rocks. So, you know, minimum viable product, focus on what matters. All right. So another thing you can turn on is generating mesh distance fields. So this is a faux ray tracing method that came out before ray tracing that Unreal can use to do some skylight shadowing. If you plan to go the lumen route, you should probably enable this setting as well. Warning, it will recompile the shaders. Here's a visualization of what the mesh distance fields actually look like. They're a mathematical representation of what a mesh is inside of a texture. And they use that to cast rays around and figure out where to do stuff in the scene. So mesh distance fields are used for lumen when the lumen ray tracing isn't available. So if you don't have a ray tracing card, turn on mesh distance fields and you'll still get the same functionality. We're going to skip the demonstration just in the interest of time. So if you do have an RTX video card or a ray tracing capable video card, it's recommended that you turn on use hardware ray tracing when available for Lumen. This will greatly improve not only the performance but also the quality of the output. It will reduce the ambient light leakage as well in the scene because the ray tracing just works better than the software method which uses these global distance fields which are somewhat inaccurate. Yes, cool. I had a demonstration thing there, didn't I? Yeah, no, that's cool. So yeah, here we have a very stark contrast between Lumen hardware ray tracing on and off. You can see this is actually just a cave that ends, it just closes up at the end, but it has a fairly thin surface. So light on the outside actually tends to penetrate through when you're using software Lumen ray tracing. But with it on, the hardware ray tracer works properly and it knows that the light is actually occluded and you don't get the light leakage that you see on the right here. Here's another example of it as well, which is a bit more subtle. You can see with it on, it's considering more things for ambient occlusion in the scene and shadowing and whatnot, but on the right, we've just got, it's harder to notice because it's such a blobby kind of indirect lighting method, so you can't really tell it that something bad has happened until you actually turn it on. Or if you're like a super talented artist and you just know. But I've talked about settings optimizations, let's talk about asset optimization. I should have brought myself a drink, some water with me. So let's talk about light assets, because this is the most important one that you can optimize on your scene. It will get you the most back for your bang for buck. So lights in Unreal can be static, stationary, or movable. Now remember, we were talking about static and dynamic before. This is basically the same thing. It's a scale of going from static to dynamic lights. There are rules that govern the light type you should use, picking depending on the performance profile you want and the dynamism that you want as well. So let's talk about static lights. Static lights bake both the lighting effects and the shadowing effects into the scene, into pre-computed data structures that you don't have to compute at runtime, so they're extremely fast. The lights will always be there. You can't turn them off unless you put them in a different lighting scenario. They'll always have the same intensity and the same color. You can't programmatically change them while your scene is running. So those are considerations that you have to make when you're trying to pick, are my lights static, stationary, dynamic? This uses a system called light mass to calculate all the shadowing for you and can take a very long time. So you might want to figure out, you might want to get your scene built up and shadowed first before you actually bake your lighting. Movable actors will still generate dynamic lighting effects, but static geometry in your scene that has static lights on them will be fully static. Static lights do not scale well to open world environments. So if you're making an open world game, do not use static lighting, do not use light mass. But you get global illumination for free. Remember, we were looking at Lumen before. This part here is the scene that where I was turning it off, it would go completely black. But Lumen is expensive. Static lighting, because you do this offline, it does it for free. You get all the light bounces. You probably get more light bounces than you get with Lumen for free, which is the big trade-off of using static lighting. You get a lot of performance back. Unreal also generates a grid of light probes for you, so that way reflections can be generated from these light probes it puts in the scene, which I'll show you in a sec. So you can still get reasonably good reflections, but they won't be that great. Yep, notice these areas in the shadow, subtly lit, global illumination. Cool. Okay, let's have a quick demonstration of that. So I've already prepared one earlier, so in a sub-level, because I have multiple lighting scenarios, so I can actually just switch to it. So I'm going to go to Window, Levels, I'm going to hide my dynamic scene, and this is actually the scene without lighting, so you can see it's just like fog and stuff. And then I'm going to turn on my super dynamic, or just super static or static. I'll just go static this time. So we'll just turn on my static. So this is a mixture of dynamic and static lights. And what you can do in here is you've actually got this show menu at the top, and you can visualize a whole bunch of stuff. So what I want is probe. You can also search it as well. So if you just click it and start typing, you can find the thing you want. And we can visualize the lighting probes. So this grid of probes is a result of the light baking process. It kind of figures out what the shading's going to be at this area, what a reflection will look like, and puts it in these static probes. And you can see this one on the right here as I move around. This is actually how we're interpolating between these probes to the result. So you see the reflection looks kind of weird, like it kind of warps between different kinds of reflection. The cave entrance goes into weird spots. But that's the result of baking your reflections down with light mass. But it makes it super fast, and it looks okay. It looks reasonably good. If I go to a little water surface down here, yeah, that looks like a reflective-y, watery kind of a thing. You can actually see, you can see all the rect lights reflecting in it as well, and they kind of disappear as I move around and walk between different probes. So yeah, it'll do all that for you. If you use light mass, you get all this for free. It just takes a very long time to pre-compute. So, let's talk about stationary lights. So remember, we had static, stationary, movable. That's our dynamic range that we can pick from. Stationary lights only bake their shadowing information, but all the lighting information is still calculated at runtime. So you get a bit of a trade-off going on. You get free shadowing, which is probably the most expensive part of it, and you still get really, really nice dynamic lighting effects, like specular and reflections are all done at runtime. Very cool. So if you're using baked lighting, this could be a really nice option to pick if you have like an actor in the foreground that you want baked shadows for, but you want them to still have all their reflections and specular and stuff still showing up dynamically and updated every frame. So I have there's a comparison image between, on the left we have stationary directional light, and on the right we have a static directional light. And you can see, as I move the slide around, how much the specular highlights and reflections change in these balls here. You can see, yeah, this looks okay, but stationary looks better because it's calculating the dynamic lighting effects at runtime. And same with this bad boy up here. You can see the reflections get much better on a stationary light versus a static light, because the static light is just using cube maps that it's interpolating between in the scene and placing all over when you generate the baked lighting. So you can see there's a reasonable difference here, but the one on the right is very convincing, so you may still pick the one on the right depending on your needs and what you need to do. Stationary lights have limitations. They can only overlap with 4 other stationary lights. Otherwise, they just get converted to movable lights in the background without you knowing. There is a optimization view mode you can pick from that little menu we were looking at before in the optimization view modes section. It's called the stationary light overlap. You get a little meter down here telling you 0 good, green good, and 2000 bad, which is white. And you can see my scene here is quite optimal. It's very green. So I've done a good job there. But red is bad. So I have a directional light in the scene that's stationary, which you can't see, but I also have 4 little spotlights that I've cast all into the same area, and you can see it now. It's giving me white, red. I've done a bad job. Those are just going to become dynamic lights, which are quite expensive. You also notice you get a little red circle on the icon for the light if it's overlapping too many other lights. So that gives you an indication that you need to go sort something out and fix some stuff up in your scene. So yeah, that's what I jumped the gun. But there you go, you can view that up later when you look at these PowerPoints. I will be releasing the PowerPoints for these slides on Learn. So, the last one we want to talk about is dynamic lights. And while they are expensive, they do have cool effects that we can use, because this is still an art technique that you can use that you want to do pretty things with. So just don't put too many of them in your scene. You can put one's great, 2, 3, yeah, that's cool. They're considered the lowest because they're the most dynamic. If a light must move or added at runtime, or has to change its color and its intensity, has to have dynamic shadows, you're going to have to use a movable light, because as you can see, I'm dragging this point light around the scene. You get some really cool shadow effects from it. because they cast those dynamic shadows. They're excellent for open world games, and you don't have to have shadows turned on for them. You can turn shadows off and they become actually quite cheap. And you can just start placing them around as little fill lights in the background. But there are ways that we can stop using things like point lights and move to things like spotlights. But yeah, and that will be the type of light that you pick. So picking the right type of light when using movable lights is super important. Ask the question, do I need a point light? A point light is, the big ball light, and it goes out in every direction. You might not need a point light. Will a spotlight actually do the same job? A spotlight is a sixth the cost of a point light, because it's only pointing in one direction, that a point light points in all directions. Because spotlights are focused and directable, you can just use them just to light just the things that you need in your scene. Because remember, focus on what's important. Your next best option is a rec light, and your absolute last option should be a point light. So, you've probably already seen this in a previous lecture. I know that you have, but let's go over it again. Use the light complexity view, and we can actually compare the different types of lights here using the light complexity view. Performance gets worse as you go from black to blue to green to red to purple. And up the top here, you can see the cone of my spotlight, and it's casting in this area here, and it's gone red and orange. We kind of accept that cost. We take it on. It's a spotlight. We need it for our dynamic effects. That's cool. And the next one here is a rec light, and you can see it kind of tops off at the edge here because it's a rec light. It basically goes 180 degrees, cast down, and that's where all the light is cast. This is the point light in the same area. Since it casts in all directions in my cave, it's basically making my entire scene very expensive. Most of the cost of what you spend in real-time rendering is the per pixel cost of what you're rendering, and most of it goes down to lighting. So the light complexity will not show the cost of shadowing, though, on a movable light, which is kind of, that sucks, but it will show you how complex it is just to run the lighting algorithm for that part of the scene. Lighting doesn't include shadowing, it usually includes things like specular, bounces, and how much diffuse it puts out, etc., albedo. So how do we figure out how much our lighting is costing us? So choosing movable versus stationary versus static. So notice there are very few differences between these two scenes, but they have massively different performance profiles. So this one on the right here, all my lights are movable, so it's the most dynamic that it can be. This is a mixture, so some of them are movable, some of them are stationary, some of them are static, so that's like picking your nice in-between. And on the one on the right, everything is static. Now remember, this is a singular screenshot, so we don't see it in motion. Motion will also inform you on what lights you want to pick, based on how much dynamism you want. But if we look at the light complexity view, we can see all of my movable lights are very expensive. My mixture of stationary and static, pretty good. I got fully black for static mode, and black is the best you can get. And that is why this is so cheap. You can see the complexity gets a lot cheaper as I move towards static lighting. This is why you need to pick the right lighting type in your scene. Wow. So the next part you can focus on is something called material optimization. How much time we got left? This one goes to 1. Cool. So material optimization is also pretty important. So every material node that you add to a material has a cost. Materials are essentially just shader code, so it has to be run on the GPU somewhere. Each line of shader code is some sort of cost that you have to pay. So we can also use something called the shader complexity view to see how expensive our materials are. And we can see here, again, green better, red bad, white very bad. Translucent objects are always very expensive. Because of the way rendering works, we're layering things on top of each other. Less things that we can layer on top of each other, the cheaper the cost is that we have to pay. So if you've got something that can be masked rather than translucent, make it masked. Masked is something like this up here where you've got gaps in your power lines. It's a masked texture. It's actually opaque and not translucent, so it actually is quite a light cost. And this, yeah, it's just totally expensive. So, one way you can see the stats about your material as well is you can click the stats button up the top here, and you can see how many instructions your shader runs. Because your material is actually a shader, it runs lines of code. The lines of code are just the number of instructions. So as you start pulling things out and removing unnecessary stuff in your material code, this number should go down. Less instructions you run, the better. The less texture fetches you do, the better. The most expensive thing a GPU can do is sample a texture because it has to pull it out of memory. Memory, if you look at a graphics card, there's a GPU chip on your board and there's some memory chips really, really, really far away from it in terms of GPU scales. It has to go all the way out there to your memory, find that texture, sample the pictures, bring them all the way back. And it's orders of magnitude. We're talking hundreds of thousands of times more expensive than just running code on the GPU. And that is just the reality of sampling textures. I'm not saying don't sample textures, just don't do it if you don't have to. Try and find ways where you can pack information into one texture rather than using 4. If you've got a specular, a roughness texture, you've got an ambient occlusion texture, they only actually need one channel in a texture, and you could actually probably put them in the RGB channels of a texture. That's one texture sample versus 3. And you can save a lot of GPU time there as well. You can use these nodes here called the static switch nodes. What these will do is they'll actually turn off parts of your code, and they'll actually remove instructions from your shader so you can fiddle with features that you want to put in. Oh, I want to implement parallax occlusion mapping, so I'll put my parallax occlusion mapping into the true part of the node, otherwise I'll put 0 into my false, and I can just click this to turn it on and off, and you can see the performance effect of having that feature. You can also make it a parameter, so you can make like a God material that has all these features in it, and when you instance it, a material instance, you can actually use this parameter to turn those features on and off, and it'll actually remove the shader code for you, making it faster. The if node in shaders is extremely expensive. GPUs are not made to do conditional logic. They're made to just sample textures, do some math, output a pixel. When you put an if node in, this is called a branch, GPUs aren't generally very good at it. They can do it, so if you have to use one, use it, but generally avoid it because it's not good for real-time rendering. Because it basically what it means is when you're sending out a pixel to be rendered, they send them out in waves of like 1,000 or whatever. They send them out in these big waves of threads that go along. If you do a branch that misses the branch prediction, so it'll try and predict what the result of the if statement is going to be. If it mispredicts that, it has to get rid of all those threads and start again. So basically, it can nuke some of the work that's been done at real time and just slow down your GPU. So avoid if statements if you can. So mesh optimization. There's a thing called nanite. Nanite is a measuring system that does away with the need for LODs. You should be aware of LODs, level of details for your meshes. It can be worse for things like trees and foliage, just about how the technology works. It doesn't like overlapping meshes, but generally it can be quite fast for super complicated meshes that are like, kind of voluminous like this, kind of like an object that doesn't have too many branchy yaddy bits like a tree. And if you turn it on, you can get automatic loading, and it works really well with the VSMs. So that's the virtual shader mapping thing we were talking about before. It's designed to run with it. And it can be really fast. But yeah, turn it on and off, experiment with it, see how quickly it runs with your project. You can build nanite per mesh, so you can turn it on and off per mesh, so you can turn it off for trees, which is nice, and still have it on in the project settings. It's generally considered to be much faster rendering pipeline for complex meshes. And it has way better results for dynamic lighting and VSMs. Cool, we'll just skip over the rest of the notes because you can read those. Otherwise, if you don't want to use nanite, you can still use Unreal Engine's loading generation tool. So if you open up any static mesh, you can set the number of LODs that it has. So you guys know what LODs are? Okay, LODs are basically the further away it meshes, it will just reduce the quality of it. It'll reduce the number of polygons that mesh has. And it has stages, and those stages are the number of LODs, so the number of levels of detail. So LOD 0 is your most detailed, up close, I'm right in front of the mesh, LOD 0. As it gets further away, as it actually decreases in screen size, it will use a lower quality version of that mesh, but it's imperceptibly low quality. So it goes away, it gets more simple to render, but yes, saves you a lot on GPU time. So, the most important part of this is we've got to talk about profiling, and maybe I should have put this at the start, but basically, all your levels have a budget. You have a time budget. So you want to target about 60 frames per second minimum, because we're going to get your stuff up onto a virtual production screen. So the way we calculate this is 1 second of time is 1,000 milliseconds. We have a frame rate of 60, and if we divide that by the number of milliseconds that are in a second, we get the resultant amount of time that we actually get to render a frame. And that results in, for 60 FPS, 16.67 milliseconds. That is how much time your level has to render. That's the budget that you have. And Unreal has several systems for profiling this. Be aware if you're preparing textures or shaders, this will affect your performance, so don't profile while this is happening. Nicely, this all happens automatically for you, and it's in the background, so just wait for it to finish and then start profiling your scene. So, the first kind of profiling we can do is something called the stat command. So if we want to profile a level and see how much time we're using, so what we can do is we can press the tilde key, which is the console, or we can access it through the viewport menu here. So we've got stat, we can start monitoring all kinds of stats. Unit time is probably the one you want. It's going to tell you all the statistics about how quickly or slowly your scene is rendering. And it gives us a millisecond output of how much time it takes to render the scene. It's recommended that you go into immersive mode, and probably better just to start, you should